All right, everybody. In this video, we're going to take a look at kind of the next section from this Solubility Notes packet. So we're going to focus here on precipitation reactions. So this is the bottom part of the second page. And the first thing that we need to remember is when we have a precipitation reaction, the general equation is we're always going to start with an ionic compound that's aqueous combined with another aqueous ionic compound. The products will be some ionic compound that's solid, that's the precipitate, along with another ionic compound that's aqueous. And so things that you can keep in mind, now there are solubility charts out there, but as a quick rule of thumb, one thing that you can remember, there are a few ions that are always soluble, and these show up quite often. So if you remember, there's an acronym that you can use, it's NAPS. So nitrate ions are always soluble. Ammonia ions are always soluble. Potassium ions are always soluble. And sodium ions are always soluble. And so that's the NAPS: nitrate, ammonia, potassium, sodium. Now, when you write out a precipitation reaction, let's take a look at this example. We're starting with calcium nitrate, so there's one of those NAPS ions, and sodium fluoride, so there's another one of those NAPS ions. So we know that those reactants are soluble. So let's write out Now, the way that I always think of precipitation reactions is it's this trading places. So the sodium trades places with the calcium, and we're going to form then sodium nitrate. And the calcium trades places with the sodium, so we're going to form calcium phosphide. When you write these formulas out, keep in mind the charges. So sodium is a +1 ion, nitrate is a -1 ion, so the ratio of ions is 1 to 1, 1 sodium for every 1 nitrate. Calcium is a +2 ion, fluoride is a -1 ion, so the ratio of ions there must be 1 calcium for every 2 fluoride, so CaF2. So now we got to decide which of these two products, if any, are solid and which ones are aqueous. So for sure, we know that this sodium nitrate is aqueous because it's got both sodium and nitrate. And if this is a precipitate reaction, that means the calcium fluoride is probably the solid. And so I'm going to circle that one as the precipitate. We want to be able to also write out a solubility expression and a Q for the precipitate. So solubility expression, that's where we use KSP in the subscript. So SP is solubility product constant. And when we write this out, it's just for the precipitate. And so we're not so much worried about these other things anymore. We're just worried about the precipitation. And so think about like a net ionic equation. If I was going to write a net ionic equation for this, sodium and nitrate, those are spectator ions. And so we end up with the product, which is solid. It's going to kind of go back and forth. Now, when this thing dissolves, we're going to get, I'll kind of rewrite this over here. This solid dissolves and makes these ions. So this is, how our precipitate would form ions. So when we write out the solubility product constant, the solubility expression, KSP, well, we're thinking about this process only. And I'm putting the solid product as a reactant, and then those ions are the product. And the reason for that is because when I write out KSP, I need to have those ions in the top, in the numerator. Notice that when this dissolves, it's F2, so that means we would get 2 fluoride ions in the solution. So that's where the square is, right? Now, Q is actually the same expression, except for this is not necessarily at equilibrium, but at some point before equilibrium is reached. So now on this next page, we're going to start thinking about if you combine two things at certain concentrations, will a precipitate form or not? In order to answer that question, again, we're going to be comparing Q to K, and this time it's KSP. And so I always like to have a visual. And so for me, the visual that works really good is this one, where we know Q and K. If Q is greater than K, and this point is equilibrium, then we're going to have to shift back towards reactant. If Q is less than K, we're going to shift over towards product. And so in terms of a precipitate forming, if we're going back towards the reactant side, the reactant is a solid. So if we're shifting back towards the reactant, if Q is greater than K, that means a precipitate is going to form. And in a solubility, the product is aqueous ions. So if Q is less than K, then we're going to be shifting towards the product, towards the aqueous. So that means it's going to be soluble. No precipitate forms. And again, the product is aqueous. So no precipitate forms. If Q is equal to K, that means we are at equilibrium. At equilibrium, we would say that that solution is saturated. Now, if Q is greater than K, that means that we're shifting back towards the reactant. And remember, the reactant, those are the solid. So that would mean that those ions that are in solution are going to come out of solution and form that solid reactant. Which means that there is a precipitate. If Q is greater than K, there is a precipitate. All right, right here we're going to actually take a look at an example problem. And the whole thing with this is the question we're asking is, will a precipitate form? And so that comes back to the discussion about Q versus K. In this one, we're going to have to look up the KSP value and then compare it to the Q value that we calculate. So let's start by writing the balanced chemical equation and determining the insoluble product. So my reactants, PbNO3, that's lead nitrate. So I know that that's aqueous because it has nitrate. Combines with sodium bromide. And at this point, I'm not worried about those concentrations. I'm just writing out the precipitation reaction. So again, we're trading places. Those cations are trading places. So we're going to end up with sodium nitrate. And I know that's going to be aqueous, along with lead bromide. This lead must be a +2 ion because there's 2 nitrates. And so over here, this lead must be a +2 ion. And so there must be 2 bromides with it. This is going to be not soluble because there's none of the NAPS ions in there. So if I'm going to write out the solubility product of this one and the Q expression, so this one, the product is Br2. That solid is going to be in equilibrium with the ions. Right? And so keep in mind that when this dissociates, there's 2 bromide ions. Each bromide is an individual ion. So I put the Br and then the coefficient is 2. Now, if I'm going to write the Q expression for this, Q is equal to concentration of lead times the concentration of bromide ions squared. And so where are we going to get those concentrations? Well, those are actually given in the first part of the problem. So we can take those and solve for Q. So Q is going to equal, we'll plug in here, 0.015 times bromide has a concentration of 0.0035. There is an exponent there. I'll get out my calculator and see what we get. So we got a number here, Q is equal to 1.8, I'm gonna round that, times 10 to the minus 7th. Now what we need to do is compare Q to K, so let's look up K. So I've got our textbook here, and we're gonna look up the KSP value for lead to bromide PbR2, and it turns out it is 4.67 times 10 to the minus 6th power. Now that we know what K is, we're going to think back to this visual that I always like to draw out. So Q is, in this case, less than K. So Q is less than K, which means we're going to be shifting towards product. And think about what your products are. Your products are the aqueous ions. So at these concentrations, mixing these two will not form a precipitate. So Q is less than K, which means no precipitate. And again, remember those product are ions, the dissolved ions. Therefore, no precipitate. Because at these concentrations, these ions are going to continue to be dissolved.